part D.2, hints for HW2, part 2, question from number 6 through number 10. Number 6. When we use the heap data structure, which of the following types of binary trees can be represented in the array as a heap? First, full binary tree. The definition of full binary tree. So if you just go back to our notes, you can get the answer. Yeah. So the answer for this one is direct answer from the notes. If you find the right notes, you can see it. Yeah. So we talk about that. Yeah. All right, so number 7, which of the following is the main advantage of the quicksort? Main advantage of the quicksort. Best case, worst case, average case, right? Yeah. So here in the introduction part, I talk about that. Introduction of the quicksort. Why? So think about why we need to develop another sorting algorithm. There must be some reason. Yeah. Yeah. So the most important reason is related to this question. So you can see. So we try to do. What do we try to do? Okay. Do we try to get the best worst case efficiency, best case efficiency, or average case efficiency? Yeah. Next question, number 8. When we calculate a to the nth, yeah, so this power function for a positive integer n, is it possible to extend repeated cubing? Yeah. We did study on repeated squaring, right? Repeated squaring, we use Horner's rule. So we represent n. We represent n using a polynomial. We get a p, then the base is 2. We can represent, use base 2. Yeah. So then, similarly for the cubing, can we represent p using base 3, right? If we get a base 3, can we use the same method, but we have to modify? Yeah, because if you change the base from 2 to 3, you need to do some necessary modification. So the question is, can we apply the similar method to get another way to evaluate a to the nth based on the repeated cubing? Yeah, because, so that method, the Horner's rule, in this way, still the fundamental idea is that repeated cubing. Yeah. Then we add some small adjustment, small necessary adjustment. Yeah. In the notes, we did repeated squaring and adding small adjustment. Okay, yeah. So here, that's just the question. Yeah. If you understand our method in the notes, then you can connect to this one. So you can try to, do the necessary modification. So think about that. Okay, all right, so that's number 8. Number 9, every heap with odd number of nodes corresponds to a full binary tree. So first, you know the meaning of full binary tree. Okay, so each node, if we look at the number of child nodes, only 2 cases, 0 or 2. There is no one child case. Okay, yeah. So look at the child nodes, 0 or 2. Yeah. So based on that, but also I like to mention the critical property. Yeah, because if you only have this, that's the definition of the full binary tree. So you may not be able to see the answer directly. So you need the most important property here. Yeah. So you can find it in our notes. So that is number of leaves equals the number of internal nodes plus 1. This formula, we have this property, this formula. Number of leaves corresponds to this case. That's the leaves case. This is the internal case. Okay, internal nodes case. Yeah. Okay, then with this property, you can answer this question. Okay, all right. Yeah. Our last question of part 2 about binary search. Binary search. Okay, yeah. So in the binary search, when we consider worst case efficiency, yeah, many times we use the asymptotic notation. Yeah. For example, the big theta of log base 2 of n. So when we describe the worst case, we use asymptotic notation. But sometimes we need more than that. We need a precise representation. So this one, so we need a precise representation. Okay, expression. Okay, precise expression. Yeah. Yeah. For the precise expression, yeah, in our nodes, I spend a lot of time derive it, prove it, right? It's a lot of work. Yeah. But if you don't want to go through the whole procedure another way, here I recommend another way. Yeah. All right. So still, one way is notes. Find it in the notes. That's one way. Okay. Second way, by experiments. Okay. Yeah. Try different ends. Try different ends. Yeah. Actually, you only need to do one. Yeah. Yeah. One end may not be enough. Yeah. Because if you use one special end, maybe two formulas, more than one formulas, both correct. That's possible, right? Yeah, for one special end. So then you try another different end. Yeah. So eventually you will get only one of the expressions is correct. Only one of the expression is correct. Yeah. So by experiments, so that's another commonly used method to give you correct answer. Yeah. All right, so that's part 2. Yeah. So we finish part 2 of part D.